Okay, so to start, we have a question from the homework. So we have this limit of a rational function, 3x squared minus x over minus 2 over 4x squared plus 2x plus 1. So does anyone know how to solve infinite limits of rational functions? We had a method to solve these types of limits. So remember, solving this limit is equivalent to finding the horizontal asymptote. So what was our method for rational functions? So polynomial divided by polynomial. Yeah, so we want to factor out the highest power of x. So in this case, it's x squared. Okay, so when we do that, so either you can factor the highest power of x or multiply and divide by 1 over highest power. Either of these are okay. So let's do factoring out. So if I factor out by x squared in the numerator, I get 3. And then if I factor in x squared from x, I get 1 over x, and then minus 2 over x squared. In the denominator, factor out x squared, and I get 4 plus 2 over x plus 1 over x squared. Okay, so since we factored out the same thing, they are common factors. Now we have this limit. Now what do we do from here? Why is this a nice form to find the limit? How do we continue this limit? Well, both of these limits exist, right? You take the limit of numerator and denominator. What do you get? Yeah, so you're left with 3/4 because all of these terms go to 0. So that's why you're left with 3/4 in the end. Okay, does that help? So the key step is to factor out the highest power of x. Because the idea is that you want to put it into a form where you can just take the limits, because these 1 over x squared, and 1 over higher powers will always limit to 0. I want to go over question 12. X and y intercepts. Okay, can we just reminder what is an x and y intercept? Like, what does that mean? Well, okay, so, okay, sure. So points where the function crosses the x-axis. Crosses, or not crosses, but let's say hits, just because touching is okay. Hits. x-axis, and or f of x hits y-axis. Okay, so can you describe all points on the x-axis? Like what are similar to all points on the x-axis? All points on the x-axis have a similar property. What's the same about all the points on the x-axis? Like, what makes a point on the x-axis? Right, the y value is 0. So everything on the x-axis has the property a comma 0. Similarly, everything on the y-axis is 0 comma b. So all points where x is 0. So the question here asks to find x and y intercepts we have x cubed plus 27, so this is the one I have, and x squared plus 9. Okay. So how do you find x-intercepts? And it's exactly what you're trying to find is all points that have the property x comma 0. So this means you set y to 0. How do you find y-intercepts? Same idea. It's all points that have the property that x is 0. So that's what you do. Set x to 0. So at this point, it's just a matter of plugging that in and then solving. So if you set y equal to 0, you get 0 is equal to x cubed plus 27 over x squared plus 9. And you notice that the denominator will never, a fraction is always 0 only if the numerator is 0. So this is equivalent to asking when is x cubed plus 27 0? And the answer there is -3. So x equals -3. And this has no roots, so that doesn't matter. So that's where so an x-intercept, or the x-intercept in this case, is -3 comma 0. So what's the y-intercept? You set x to 0. So y is equal to 0 plus 27 over 0 plus 9. So that's 27 over 9. What is that? 3? So 0, 3 would be the y-intercept. Is that okay? Does that make more sense after seeing that? Okay, great. Yeah, so whenever you have x and y intercepts, this is always the method you do. Set x equal to 0 or set y or f of x equal to 0, respectively. Okay, so yeah, so any other questions? Vertical asymptote. So this one actually doesn't have a vertical asymptote, right? So vertical asymptote. So vertical asymptote is when the limit as x approaches a from the left, or the limit as x approaches, oh sorry, that was the right, from the or the left, is infinite. Then asymptote at x equals a, vertical asymptote. Are there any problems with this function here? X cubed plus 27 over x squared plus 9. Are there any places where you think there might be infinite limits? So in a rational function, where might you expect a vertical asymptote to occur? Right, so for rational functions, vertical asymptotes only might occur, not always, but might occur, when the denominator is 0. Can someone give an example of when the denominator is 0, but there is not a vertical asymptote? Right, in the case of a whole. But in this case, we see that there's no problem with this function, right? There's not even a whole or a vertical asymptote, right? Because x squared plus 9 is never equal to 0. So there's no vertical asymptote here. Do you see that? So the question is, if there is a vertical asymptote, where might it be? Or where must it be? It must be where the denominator is 0, if it exists. However, the denominator is never 0. So that means it cannot exist. Is that okay? Okay, good. And yeah, of course, the next thing you would do if you could solve for x in the denominator would just to make sure when you factor there's nothing canceling, because when something cancels, then that's where a whole exists. But if nothing cancels, then you're okay. Okay, so why don't we move on for today? So last time we talked about various derivatives of functions at some points. Went as far as discovering the power rule. So now let's kind of take a step back and say, okay, well, how can you identify what the derivative looks like as a function itself? Right. Last time, remember, we were finding the derivative at a point everywhere, right? Like the derivative at a point was the limit as x approaches a of f of x minus f of a over x minus a. So the idea is, okay, let's pretend a is just the variable. It's like whatever you plug in for a, then you get the derivative at a. So I can understand what the derivative of a is, the derivative of f at every point, and then map those values and get a function. So let's talk about what the derivative is, and then see if we can understand how to graph the function that's called the derivative. Okay, so yes, this is the technical definition, but does anyone remember the kind of the graphical definition of a derivative. Like, how can you draw it here? Like, what do you draw and measure for the derivative? And think about how we kind of developed it. Right, it's the tangent line. And what is the derivative specifically? So it's definitely related to the tangent line. Good, it's the slope of the tangent line at that point. So, but as long as we're able to draw tangent lines, and we know when slopes are positive and negative and how big they are, right? Then we can kind of sketch it. So let's look at this point, and let's draw the tangent line. So if we draw the tangent line, looks something like this, right? Can someone tell me something about that slope? Is it positive, negative? Is it really big negative? Is it really big positive? Right, it's negative. And is it close to zero negative or really big negative, like negative 100 or more? Okay, so let's kind of identify what does a zero slope look like? Zero slope line. Is it vertical or horizontal? Right, it's horizontal. Now, actually, what is the slope of a vertical line? Yeah, there is none, right? And there's a couple of ways you can see this. You know, based on the definition of the derivative, right? Oh, yeah. So I'm recording it and I'll post it on YouTube, and then I'll send you the link to it. So first of all, this is not a function, right? X equals a is not a function. So I can't talk about the derivative this way. I mean, let's not use a. Right? The derivative requires a change in y and a change in x. When you have x equals b, which isn't changing? What does not change in the line x equals b? Like, think about on the horizontal line, what doesn't change are the y values, right? So what doesn't change in the x values? Or, well, I just said it. X values do not change, right? So this is always 0. So there's never a change in x. So the derivative doesn't make sense. Okay, so that's important because so how do we look at this line here? Well, it's pointing downward, right? If you draw your little person, it's pointing downward, but it's very steep. So that should tell you it's going to be like really negative, right? And if you think about it, based on the curve here, if I go further to the left, do you think it's going to get steeper or is it going to flatten out? If I look higher. Well, it may not remain the same because this is kind of like curving upward. Not necessarily that harsh of a curve, but it's still expanding outward. Um, so it's actually it's hard to see by the graph, but if I drew it a little bigger, maybe. So the idea is that as you expand outward, it gets steeper. So it's kind of hard to draw it because so it's going to be steeper as you go outward. So does that make sense? Like, as you go outward, it's going to get steeper and steeper, almost like to a vertical line, but never quite a vertical line. Okay, so let's look at other places. How about here? Let's draw the tangent line. Any properties of this tangent line? Is it positive, negative? Is it close to zero? Or relative to, so yeah, it's still negative. So relative to the one before, is it closer to zero or further away from zero? Yeah, it's closer to zero. Okay, so now let's keep on going. Now what happens when we hit zero? What do you think happens? What's the slope there? Yeah, the slope is zero. And notice that as you're getting closer and closer to zero, the curve narrows out. So how is it changing? Well, it's starting to the curve is starting to flatten out. So that's why we're getting closer to zero. Okay, so now what happens as you start going on the other direction? Right now you're pointing upward, right? Your person is going up. So the slope is increasing and it's positive. And as you go further up this, think of it as like an infinite half pipe, like with skateboarding. What's happening to the slope? Is it getting bigger or small? Right, the slope increases. So this is just a rough sketch of the derivative, right? There might be, depending on how I drew it, it might look different, but that's the rough idea. So any questions just on the basic idea of sketching the derivative this way for this function? The main thing is to understand when a tangent line's slope is positive, when is it negative, when is it zero, and how to determine if it's which slope is greater than or less than. Okay, so let's do another example. Okay, so let's do this. Okay, so when we start over here, draw this tangent line. Okay, what is the slope here? of the tangent line. Yeah, it's positive. And is it big positive or is it small positive? So small means closer to 0. Do you think it's closer to 0 or, yeah, it's actually big, right? Think about like if you were to climb this as a mountain, it would be pretty difficult, right? So that's actually big positive. Now, but what happens as you get closer? As you keep climbing up, what happens? Yeah, it's still positive though, but it's closer to 0. What happens at 0? Yeah, so the curve is flattening out and flattens out at 0. And what happens if you move forward? It starts increasing again, right? Does this curve ever decrease? No. So it might look something like this. All right. Everyone see that? Okay. Any questions about this? Everyone see the kind of method here? So the tangent line drawing is very important. It kind of tells you how much is it increasing or decreasing. Okay, let's do another one. Let's be a bit more interesting. Okay, how about this one? Think about a tangent line over here. Well, first of all, what does the tangent line look like over here? Like, how do you draw the tangent line? By the way, these are flat lines. There's no curve to them. So how do you draw the tangent line at that point? Yeah, so not only is it parallel, though, it's coincident, right? Because parallel lines, if two parallel lines share the same point, then they're coincident. Now, what's the tangent line here? Same thing, right? It's also on that line. What are the slopes of these two lines? Yeah, they're equal, and are they positive or negative? Yeah, they're equal and positive. So as you move along this line on the left, does the derivative change? No, right? Since the slope is the same for all points, The derivative must be the same for all points. Okay, so we're going to skip over 0 for now, and let's look at the other side. Now, same idea, right? This is also a line, so the tangent lines are going to be the same. But in this case, are the slopes positive or negative? Yeah, these are negative. Okay, now, what happens at 0? Yeah, the function exists at 0, it's a point, but like, how about the tangent line? Yeah, it's going to be hard to talk about tangents there, right? As we get closer to 0, it behaves like this is the tangent line, right? As we go to 0 from the left. But as we go from 0 to the right, this looks like the tangent line everywhere, right? So there's no way to understand exactly what's happening at 0. So the limit doesn't exist here, right? Limit left does not equal limit right. So we did this one. This kind of looks like the absolute value one that we did last time, and why this limit did not exist. So how do you represent that on the graph of the derivative? Yeah, so the discontinuity, so there's going to be 2 open circles, right? Because f prime of 0 does not exist. Does everyone see that? Okay, good. Okay, let's do another example. Okay. Here's f of x. Let's think about f prime of x. Okay. What is the derivative here? It's positive, right? Let's put it up here. Now, as you start going up like the mountain, what's happening to the derivative? Is the derivative increasing or decreasing? Right. Its approach is 0, but it's still positive. So it approaches 0. Because at the top of the mountain, it's 0. Now what happens when you start rolling back down? What is the derivative? What's happening to the derivative? Yeah, it's decreasing. decreasing and it's negative, right? Um, Now, when does it decrease forever, or when does the derivative start increasing again? Like, so when I go down here, it's the derivative decreasing. Then when does it start? When does the derivative start going back to zero, if at all? Probably when the curve flattens out again, right? Like here. Do you agree, do you agree that the derivative is zero here? Yes, no? Okay, good. So this is coming back up. So now, okay, let's think about this. Why does this turn? Well, where is the, so think about like, so what does this point tell you? This is where the curve is decreasing the most. So if I delete some of these tangent lines, and just ended up deleting the whole thing. You can think where is the curve decreasing the most? Well, it's where the tangent line is most steep. So maybe that's like right here, where tangent line is most steep. Okay, so what happens in the when we finish the curve? Is the derivative positive or negative? Positive. Okay, any questions about that? I have a question for you. So if this says where the curve is most steep, well, what does that mean? Let's say we take the derivative again. Right? When what do you think the derivative is at this point here? So now forget the original function. Yeah, so if you draw a tangent line here, right, it's zero. So let's it down here. And now, how about the derivatives on either side? What's the derivative here? Zero. Now, how about as you start going from this zero to this zero, what are the tangent lines? Are they positive or negative slope? Intermediary ones. Right, they're negative. And similarly, there's some point where it gets too negative and then starts coming back up. Now, as you come back up, are these tangent lines positive or negative? They're positive. But what happens when you complete the curve? It goes back to 0, correct? Okay, so this would be the derivative of the derivative, right? So what does this tell you? How much is the derivative changing? So let me ask you a question. So remember when we started talking about the derivative, well, even before that, we started talking about limits. If your original function was like position, what was the derivative kind of telling you about? Like, what is the derivative of the position function? It's right when we first started talking about limits. So how much is position changing? What should that tell you about what it's calculating? What sort of thing tells you how much distance is changing? Like a physics thing, like how is position changing? Correct, speed or velocity. Right, it's velocity. So if you look at the picture, right, if this initial picture is telling you the displacement of an object or something, this picture would tell you what the velocity is. So, and that makes sense in the picture, right? As you go up, right, you have positive speed, right? And then once you hit this topmost point, you start coming back down. So that's why your speed is decreasing. Think of it like as an oscillating. You're starting to come back to your original position. This is your original position here. And your speed is pretty negative. And then you are pretty far away from where you started, but that's where the speed levels out, and then you start increasing again. So what do you think the analog would be for the second derivative? How much is velocity changing? What's the physical analog to how much velocity is changing? Or what is that word called? How do you measure how much velocity is changing? Yeah, acceleration. So these really have physical applications. So the acceleration is just the derivative of velocity, and it's found in the same way. The limit as x approaches a of instead f prime of x minus f of prime of a over x minus a. This is acceleration. So any questions about that? Okay, so let's think about this acceleration and see how can we identify it just by the graph itself and not having to go through the second derivative. Okay, let's do this graph again. Okay. All right, so what does the second derivative do? So, well, to think about the second derivative, let's first recall what the first derivative is. So in our sketch, it looked something like this. And let's see how we can understand this based on the original graph. So, how is the first derivative changing? Well, notice that to the left of this line is the derivative positive or negative. Derivative of the derivative. Like if you draw tangent lines, is it positive or negative? It's negative, yeah. Now to the right of the line is it positive or negative? It's positive. So that tells you that in the derivative, and that's why we have this shape here. We had that's why this is negative, and this is positive. Right? If the derivative is negative here, that means we're below the x-axis. If the derivative is positive here, that means we're in the positive part of the plane. So we had said this is the place where the derivative is really big and negative, right? Largest or really smallest, most negative, most negative velocity. So that was pretty much where the slope was steepest. So to understand what the second derivative is, if you look at the property of this graph here, the second derivative tells you what the shape is. That's the idea of the second derivative. The second derivative tells you the curvature. Or a shape of the graph. So when so if you think about it, like um, when you start moving, you're at the you're going really fast, right? And that's the fastest that you've gone once you start. As you continue to move, you are decreasing in speed, right? Relative to where you started, your speed is decreasing. So that's why it has this shape here. Everyone see that? So relative to um, relative to the starting point, speed is decreasing. Everyone see that? Like the tangent lines are getting less and less steep. And then on the other side, so that's why it's negative. Acceleration. And now what happens when you look at your most steep point? Relative to this most steep point, what is the speed doing? Speed is increasing, right? These tangent lines are getting less and less negative. So relative to the most steep point, tangent lines are getting less steep. So in other words, the slope is increasing. So that's why it's positive acceleration. Everyone see the kind of the idea there? So it measures how much is the speed changing, or in other words, it measures how much are the tangent lines changing. How are the tangent lines changing? Okay, no questions. So we'll just define what we just described here. If the second derivative is negative on an interval, the function f of x is called concave down. If it's positive, on an interval, sorry, on that interval. F of x is concave up on that interval. So what does the second derivative tell you? It measures the concavity of a function. So the general shape here is concave down. But there's this point here where it stops becoming concave down and starts becoming concave up. So it's kind of silly, but concave down makes a frowny face and concave up makes a happy face. So that's the idea with concavity. Any questions about that? So this turning point is the derivative is equal to 0, second derivative. Questions? Again, if you're uncomfortable with concavity, it's okay to go through the derivative and then to the second derivative. Questions? Is everyone following? So someone give me a yes or a no. Okay. Yeah, but feel free to stop me. Do you have to go to the first derivative to the second? So this is kind of the way to go right to the second, is to kind of look at it based on concavity. When we actually start doing functions, like calculating like the actual equations, we have to go through the first derivative. But if you want to just like kind of identify where the second derivative is positive or negative, then this is a way you can do it just by looking at the picture. Yeah. So speaking of that, let's kind of go back to our functions. So calculating derivatives. So last time we did a whole bunch of derivatives that led us to very, very nice formula, power rule. This was last time. That if f of x is equal to x to the n, then f prime of a is equal to n a to the n minus 1. Or f prime of x is equal to n x to the n minus 1. I remember that we did that last time. So that's what we did last time. So now we want to, let's suppose we have this rule, f of x equals the power rule here. But what's the derivative of f of x is equal to x to the n plus x? Right? We don't have a rule that tells us how to find the derivative of a sum of two things, right? Not yet, at least. However, it would be really nice if there was a rule, you know? I probably don't want to do the limit definition of this if I already have a already proved for ourselves a limit definition of this. So as a motivator, so we're going to prove this limit, this derivative law, the sum law. So let's say you have f of x and g of x have existing derivatives f prime of a and g prime of a. The goal is to find f plus g prime of a. So we want to, so what we're going to be doing today a lot is what properties do the derivative have? Does the derivative have? This is a new type of thing that we've discovered. So we're trying to find some properties. Okay, so how do I find the derivative? If I don't know any rules, what is the definition of the derivative? And remember, there was two different methods, right? Yeah, slope of tangent. So how could you do that? So the slope of the tangent line is the limit of the slopes of the secant lines. So yeah, so these are the secant lines, slope of secant lines. And then taking the limit of them gives you slope of tangent line. Okay, good. Okay, so what is f plus g of x? Well, it's just f of x plus g of x. That's how you define the sum of two functions. Okay, what do you do from here? So I want to, the idea what we're doing here is we want to put this into a form of things that we already know, right? What do we know is that we know that f prime of a is a thing and g prime of a is a thing. Do you see f prime of a and g prime of a in this expression here? First of all, what is f prime of a? Sorry, that was probably a lot to type out. But it's this, right? But just with f of x. F of x minus f of a over x minus a. And then what's g prime of a? It's g of x minus g of a over x minus a. So do you see these in this limit here? Here's f of x minus f of a. And here is g of x minus g of a. So let's put them together. Okay, so what could my next step be? How do I get these expressions? This is what I want, right? I don't quite have that, but I'm close. But what can I do to get these expressions? What step do I need to make? Yeah, so I want to rearrange fractions. And how do you do that? Just by splitting it up. So f of x minus f of a over x minus a. Then group that alone, and then g of x minus g of a over x minus a. Okay, so now we have that limit law that says, since these limits exist, because we said they existed, then we can do the limit of each of them. Okay, and that is exactly f prime of a plus g prime of a. Okay, that's great. So now, what does this mean? What is the derivative of, let's not use x to the n, let's say x to the 7th plus x squared. What's the derivative of x to the 7th plus x squared? Right, so now we have established that the derivative of a sum is just the derivative of each part in the sum. So, well, not squared, but 7x to the 6th, right? And then plus 2x. Yeah, so each of those individually is a power rule that we established before. And now that we've determined that the derivative of the sum is just the sum of the derivatives, then it's easy as just taking the derivative of each. So that really expands a lot of derivatives, right? Okay, so let's do another law. So if you recall from last time, maybe it was, no, it wasn't last time, but a couple classes ago, we did this. The limit as h goes to 0 of sine of x plus h minus sine of x over h was, do you remember what this is equal to? We did this limit a while back. We found that this is equal to cosine. So same as limit as x goes to a of sine of x minus sine of a over x minus a. And then, right, so these are both the same, these are both the derivative, right? And so this one has an a in it, so this would be cosine of a. But if a is your variable, then you just make it cosine of x. Everyone vaguely remember this? Okay. So if we know that, let's say if we want to find the derivative of f of x is equal to x sine of x. Now, same conundrum. I don't want to go through the whole limit definition again. I see that this is something I can easily take the derivative of. And this is something I can easily take the derivative of. So surely there should be some rule that allows us to find the derivative of this. So that's going to be our goal, is to let's actually find a rule for this. So let's do it. So if f prime of a exists and g prime of a exists, find fg prime of a. So first of all, if you remember, fg of x is equal to f of x g of x, so that's what we're going to be using. And let's do the limit. Limit as x approaches a of fg of x minus fg of a over x minus a. The same deal. This becomes limit as x approaches a of f of x g of x minus f of a g of a over x minus a. Okay, something's a little, it's going to be a little bit tricky now, right? Because I can't really factor anything, right? So we're going to do a neat little trick. Is that, let's just look first at f of x. So first of all, what do I want? I probably want to find some f of x minus f of a over x minus a. And I probably want to find some g of x minus g of a over x minus a, right? But the problem is I have, what's in front of x, f of x is this g of x, right? And what's in front of the g of a is this g of a. So, but what I can do is I can force factors, force in factors. So let's think about that. If I have f of x g of x minus f of a g of a, let's do this trick by saying, okay, let's have f of x g of x, and let's add in a term. So let's add in negative g of x f of a, and then plus g of x f of a. Everyone agree that I can add that term in? Why can I add that term in, by the way? Yeah, so the idea is I'm going to factor. Right. Well, nothing gets canceled here, but so how am I allowed to just do this in the first place? Like, aren't I changing the function? Or why am I not changing the function? Yeah, it doesn't change, right? This is just equal to 0. This is a neat trick in math. Um, if you can change an expression as much as you want, as long as all you're doing is adding 0 or multiplying by 1, and that's okay. So why is this good is that if I rewrite the expression and group it, then things do factor. Can someone tell me how do you factor the first one? How do you factor this? Yeah, factor out the g of x. And what's left over is f of x minus f of a. Oh, how convenient. And then what do you factor out of here? Or not f of x, but f of a. But yeah. Okay, so now let's bring this back into our limit. And then maybe you can see how you rearrange it and see where the formula comes. Okay, so what is that? So we have secured these terms. So we can split up the fraction, right? Okay, so while I'm writing this, can someone tell me the limit? Oops, I jumped the gun. Oh, no, it is that. Yep. So this is the expression exactly for f prime of a. And then you plug in a here, you get g of a. Plus, plug in, this is exactly the expression for g prime. And then you have f of a. So this is equal to fg prime of a. So this is called the product rule of derivatives. And just to make sure, I wouldn't expect you to develop these proofs on your own. For this class, all you really need to know is the rule itself. So let's rewrite it in terms of functions. Fg prime of x is equal to f prime of x, g of x, plus g prime of x, x. It's the product. Okay. So, questions about this? Again, these are good limit practices. That's why, one of the reasons why we're doing this all out. And also, it's nice to know where these things come from. They're not just random formulas out of the blue. Okay, so let's do that derivative we had before. So we had x sine of x. So by the way, just for this class, sometimes I'll use this notation for derivative, d over dx. Sometimes I don't want to write f of x all the time. So this means take the derivative of. Take the derivative of. So I just might write that instead of that whole sentence. Okay, so how do I find the derivative of this? Well, I realize it's a product of two things that I know the derivative of, right? So what's the derivative of x, and what's the derivative of sine of x? So the derivative of x is just 1, right? And then what's the derivative of sine? Oh, I don't need to take the derivative, right? It's sine of x. And then what's the derivative of sine? Yep, cosine. And then it's just f of x, no derivative, so it's x. So what's the answer? It's sine of x plus x cosine of x. All right, everyone see that? Okay, great. Okay, let's see. Okay, let's do well, let's just do the derivative of cosine while we're here. So kind of going backwards. So let's use the difference quotient definition. It's easier for this, for sine and cosine. So remember the difference quotient definition is the limit as h approaches 0 of f of a plus h minus f of a over h, right? This is equal to f prime of a, right? So let's do cosine. Limit as h goes to 0 of cosine of a plus h minus cosine of a over h. Okay, I remember the sum formula for cosine? Okay, not, that's okay. It's cosine of a, cosine of h, minus sine of a, sine of h. So cosine of a, cosine of h, minus sine of A sine of H, and then minus cosine of A. This is all over H. Okay. What should I do here? I probably want to group things together and probably group some nice limits together. Can someone tell me a nice limit I might want to group alone? What is this? What is the nicest limit you see here? This should be immediate. Ringing so many bells. Yeah, the sine of H over H. Right. This should ring a lot of bells. So let's keep that term and put it outside. So cosine of A, cosine of H, minus cosine of A. Let's put this over H, and then let's leave it outside. Sine of A, sine of H over H. Okay, so what we can do here, these both have a cosine, so let's factor those out. So it's cosine of A, then limit as H goes to 0. Right, I can factor out the cosine of A because it doesn't have an H. Then I have cosine of H minus 1 over H. Okay, how do you solve this limit? I did this limit before, so don't treat it as a formula, but how do you solve it? Do you remember? It's Quiz Thursday. Question like this may not pop up, but yeah, multiply by cosine H plus 1 because you realize that looks like the difference of two squares. Okay, so that makes you cosine squared of H minus 1. Can someone tell me what cosine squared of H minus 1 is? It's almost sine squared, but it's a little bit off. What's sine squared? It looks like this, but it's a little bit different. Right, it's negative. Sine squared it would be 1 minus cosine squared, right? So it's just the reverse. Okay. So we have minus sine squared. Not that it really matters in this because something happens. Okay, how do I continue this? How do I continue solving this limit? I'm going to group something, right? Group a nice limit. Yeah, so I can group out the sine squared h, but why don't we just skip right to just factoring out the thing I want, right? Let's just factor out the sine of h over h. That's the thing I want, and then let's leave the other stuff on the side. Okay, cool. So what is this limit to? What's this limit? A limit of a product that both exist, which is the limit of each. One, correct. How about the other one? What is this limit to? Yes, 0. Again, why is it 0? Is because the denominator is 1 plus 1, so there's no problem with the denominator. So this whole thing is just 0. Okay, so what does that mean? That all we're left over is the other part. Limit h goes to 0 of sine of a, sine of h, over h. And what's this limit? So this it's just sine of a. So this is 1. This limit is 1, and then the answer is negative sine of a. Okay, great. So what is if f of x is equal to cosine, what is f prime of x equal to? We just determined it's negative sine of a. So any questions on that? Again, it's not something I'm probably expecting you to do, but all the mini limits inside are things that I'm probably expecting you to know how to do, like using the sine of h over h, or if you just replace those with x's, it's the same thing. So just be aware of that. So this entire limit I wouldn't expect you should do, but the limits in between are things that you should be somewhat comfortable with. Okay, so yes. Oh, let's make it a. X. So the other one we did before was if g of x is equal to sine of x, f prime or g prime is equal to cosine. So these are some laws that we have, or formulas. Okay, so let's find the derivative of sine times cosine. Okay. So what's the product rule say again? So it's the derivative of the first function times the second function plus the derivative of the second function times the first function. So you can see this is why I like this notation sometimes better, just because it's easier to write all those things out. Everyone agree that that is the product rule? Just written out a little bit differently. Okay, so now just plug it in. Right, the derivative of sine is negative cosine, and then cosine. And the derivative of cosine, oh, sorry, not, the derivative of sine is just cosine. The derivative of cosine is negative sine times sine. So this is cosine squared minus sine squared. What is cosine squared minus sine squared? Anyone know? Not quite 1. If it's plus, that would be 1. It's not minus 1 either, because this would be minus 1. That would be minus 1. It was, this is a double angle formula for cosine. Yeah, cos 2x. Okay, cool. Let's do another one. Let's do d dx of sine squared. Okay. How do we do this? Using what we know, not any future rule. There are other rules to solve this, but we don't know them yet. Yeah, so product rule, so let's treat it as a product, not as a power. Again, there are other rules to deal with it as a power, but we don't have that yet. You might prefer this one better when we do this. All right, so it's the derivative of the first times the second plus the derivative of the second times the first. So they're the same. Okay, the derivative of sine we established was cosine. So it's the same thing. So this is 2, say, sine cosine. Anyone know what 2 sine cosine is? Yes, this is sine 2x. All right, cool. While we're here, let's do cosine squared. Okay, so similar idea. Cosine, cosine. So derivative of the first times the second plus the derivative of the second times the first. So derivative of cosine we established was negative sine. And derivative of cosine is negative sine. So, how many sine cosines are there? There are negative 2 of them. All right, and then what is negative 2 sine cosine? Yeah, negative sine of 2x. So that's one way you can express this. Another way you can express it is sine of negative 2x. Can someone tell me why you can express this as negative sine of negative 2x? Do you remember a property? Yeah, that's true. It's sine of negative x is equal to negative sine of x. Do you remember what that property is called? So, not multiple. So, I can't just bring in any. This is not true, right? A sine is not equal to sine of ax. That's what you mean by multiplication property. But it's because of the negative. Since it's negative, you can bring negatives in sine inside of sine. It's a symmetry law, right? Sine is an odd function. Do you remember what odd means? When you plug in a negative, get the negative of the positive. A way to see that is by the unit circle. If this is angle, and this is xy, when you look at the negative of the angle, you're just reflecting over the x-axis, you get x negative y. So that's why sine is odd. This also is why cosine is even. Know what even means? Right. When you plug in the negative, it's the same as plugging in the positive. Okay, cool. So we did a bunch today. I'm not going to go through the proof of this next one, because it's going to probably take too much time. But maybe we can talk about like what your approach would be, or motivation. What sort of law do you think you would want to create in order to find the derivative of tangent? Like, I don't want to do the whole limit definition of tangent, because tangent's kind of an annoying function, right? But how can I express tangent in functions that I know, and then maybe develop a new type of law in order to deal with these types of functions? So, in other words, since I know that tangent is a quotient, what I want to do is come up with a law. Come up with a law of the quotient of two functions. So maybe I'll set it up and see if, if you're a little ambitious, you can kind of figure out yourself. So do one of these. So you want to put it into a form where it's a nice expression of the others. And I'll tell you what it should be equal to and see if you can do it. It'll be f prime of a g of a minus g prime of a g prime of a f of a over g of a squared. So as you can tell, it might be a little bit more complicated of a proof, but it turns out to be okay. Yeah, so I recommend you trying to like work your way through the proof. And if you don't want to do that, maybe use this formula to find the derivative of tangent. But I recommend kind of trying to go through yourself, kind of emulate how we did the product rule. We did a couple little tricks with the product rule. Right? The big trick in this one was adding this extra term in here. So maybe you have to do something similar for this one. Yeah, so just try it out. And if you don't want to do all that, less ambitious, just use the formula on tangent. Yeah, this is being recorded, so it'll be uploaded to YouTube later today. And speaking of which, I will stop recording.